Here we'll be taking a look at a nice application of ARIMA models. We'll look at the quarterly percentage changes in the US consumption expenditures. Now you can download these series of personal consumption expenditures on your own from the FRED website and calculate quarterly changes, or you can just download the CSV file. A good idea would be to actually compare this file with what you get from the website. Now, although this is a quarterly series, the personal consumption expenditures typically do not display a seasonal pattern. And so we'll think about what to do when we are constructing ARIMA models or when we are trying to build our model. The first thing you want to do is, once you've read the file, you want to take a look at it. But what would be necessary is to convert that as a symbol and tell R that this is actually a quarterly time series. So that's what we're doing here, and this is what the plot looks like. Now, if you wanted to fit a model, an ARIMA model, automatically, you can do it by using the ARIMA function within model. So anytime you are fitting a model, you remember you have to write down model, and then you have to write down ARIMA. Now, since we are not focusing on the seasonal component, this will actually be explained later. Whenever PDQ is written in capitals or uppercase, you have, this is a representation of the seasonal component. So we are really in this line of code here, we are saying that run the automatic ARIMA, tell us what the ARIMA model is, but make sure there is no seasonal model that is being estimated simultaneously. So with saying PDQ is 0, 0, 0, we are imposing a no seasonality condition because the data appear to be non-seasonal. Now you may just want to run it without that, okay, and you can do so. But let's take a look at what does the result tell us. So the result tells us that the best model for this type of data is going to be ARIMA 103 with mean, okay? So what you have here is are the parameters associated with the autoregressive component. So if you have yt minus 1 in the regression, which is your AR1 component, that has a phi of 0.588. If you have an MA1 component, that has a theta of theta 1 of negative 0.35. If you have a epsilon t minus 2 component, which is your MA2 component, that has a theta of 0.08, and so on and so forth. And then you have a constant, and you have an estimated variance for your errors as well. So if you want to write down this model, then that is going to be looking like this, where yt equals 0.307, which is your constant, okay, plus your lag value of y with the phi parameter, which is from here, 0.589, minus the component, the parameter that you have estimated for your MA1 component, which goes here, your MA2 component goes here, and this should be MA3. There's a typo here, but this is that component here, okay, plus epsilon t, where epsilon t is a white noise process with the standard deviation of square root of 0.35, okay, which is coming from right here. So this is how you understand what the output is. Now you can then, once you fit the best model, this is really R doing all the work for you. You haven't done anything yet by looking at the autocorrelation functions or partial autocorrelation functions and doing some guesswork into what type of model would actually fit this data the best. You can, if you're just using the automatic method, then you can just forecast 10 periods ahead. This is quarterly data, so you're estimating about 2.5 years. And you're using the slice function. I'll post more on the slice function later, but you can also take a look by doing question mark slice or question mark ggplot and then looking at what the slice function does, but it does plot a subset of the data. Okay, that's what it's doing here, along with the forecast. So you have a forecast that is represented here and the 80% and 95% confidence bands. And it does look like you have large prediction intervals here, which is standard for a lot of the economic and financial data because it's very hard to forecast. Now, there are some caveats to understanding ARIMA models with different types of values given to the constant and the differencing term and what will happen to the long-term forecasts. You can take a look here. One thing to remember is that as the value for the differencing parameter increases, the higher the value of D, the more rapidly the prediction intervals would increase in size. So the more you have to difference, the more the prediction intervals would be larger. For D equal to 0, when no differencing is required, the long-term forecast standard deviation would go to the, or would tend to the standard deviation of the historical data. Similarly, for cyclic behavior, there are other types of restrictions that we don't need to go into detail about for now.